So, welcome to EE252 electronic devices and circuits. Before I start the lecture, please make sure that you type your E number, first name, and last name in the chat box for the attendance purposes, right? Your name, sorry, the E number, like E18210 or whatever, first name and last name, whatever the name that you like you to be called, like one runaway request. Okay? So make sure that you type that. I will take that as the attendance for this class. Okay, so do you have any questions from the previous lecture? Any questions before I start this today's class? No questions? All right, good. So the last week or the last class, we looked at basically the different modes of charge motion. We said there are two. One is drift, the other is diffusion. We said the drift was well characterized by the Ebersmall model, where we can relate the voltage applied across the PN junction and the current through it, irrespective of whether the direction of the current, direction of the applied electric field is in the direction, of the forward direction of the junction or not. Okay, so that was the Ebersmall model, and also we said the diffusion, however, did not, diffusion had electric charge moving in all the directions, including the direction which is opposite to the applied electric field, right? Applied voltage. So we call this current the diffusion current or reverse saturation current, IS, and that IS depended on many external factors, including the temperature and few other possible things like the availability of photons and some external energy sources. So unfortunately, these external energy forces, energy fields, did not get captured in the Ebersmall equation. So therefore, the Ebersmall equation we could not use to describe this diffusion based activity. The IS depended on this diffusion, and how IS changed depends on any external fields, right? So therefore, that is where we stopped. Okay, we said also that while the heat is one way of increasing the IS in order to increase ID, but when you increase the heat, it also gets absorbed by the atoms in addition to electrons. So when the electrons absorb heat, they have higher energy, so they can move faster and overcome the depletion layer. But since atoms also absorb this energy, they vibrate and make the resistance to current higher. So that what ends up happening is when you apply the electric field in the negative direction, the depletion layer increases. So therefore, the resistance also increases, and the current does not actually go up. And also, if you try to use thermal energy or the heat to increase IS, what ends up happening is basically a thermal runaway due to the increased heat dissipation at the junction. However, if you use photoelectric effect, where you use only photons to excite the electrons, the energy will not be absorbed by the atoms, but only the electrons. So the electrons will have a higher energy to overcome the barrier, the depletion layer, so that the conduction will go up, and therefore IS will increase without increasing the resistance or the heat. So therefore, that we identified as a potential way to increase IS without affecting the resistance. However, this phenomenon did not get captured by Ebersmall model. So therefore, we need some other way to characterize such external fields. Okay. All right. That's basically what we talked about last time. And today we are going to talk about some transistor semiconductor physics. I'm pretty sure you talked about these things also under under semiconductor physics, the basics of this. But let's try to capture what is very important for this part. Okay. Any questions so far? You guys can clearly hear me, right?
Yes, sir, we can.
Okay, thank you. All right. So now what happens is basically when you want to form, or we call fabricate a transistor, right? Or even a diode. What we do in a diode, what we have is a junction between an N-type and a P-type semiconductor, right? So we mentioned repeatedly that this junction cannot be made by producing two semiconductors, one N-type and one P-type, and bringing them together to form a junction. That will not work. The reason for that is the microstructure at the boundary will be large and it will not create a good enough contact, right? So therefore, it will not work. However, if you want to create such a junction, what you do is actually you take a substrate, let's say an N-type semiconductor silicon wafer, right? So that this whole silicon wafer is doped with N-type material, right? So that, like, for example, phosphorus, right? And then if you want to create a junction, then you need to have a P-type area. In order to do that, what we do is we expose this N-type semiconductor to the specific type of dopant or the impurity. For example, aluminum wafer. Okay, so if you already have an N-type substrate, and if you make this surface exposed to aluminum wafer at high temperature, what will happen is that aluminum will get diffused into this N-type substrate, making, say for example, if I have this as my substrate, let's call this the N-type substrate, then what I do is I make this exposed to the aluminum so that it diffuses into this substrate, forming a P-type layer, P-type semiconductor. So that you have now an NP junction. Okay. So now if I have a metal contact, this is a metal contact between this and, let's say, this area here, then you have basically a diode. Now, if you want to create a transistor, what you would do is basically you would add another layer, right? Another, you infuse, diffuse again some N-type, right? So to do that, what you would do is basically you insulate some of these areas, right? For example, here. So this is silicon dioxide, right? It's a insulator, so that when you expose it again to, for example, phosphorus vapor, it will not get into this covered area. And when you expose it for long enough, then again it will create another layer inside this, which is of N type. And then what you can do is you can put another piece of metal and connect it, and then you insulate this other areas. So this whole thing is insulated. Let me. Okay, so something like this. Okay, so this is how you actually create the transistor. Now, this substrate, we can call this the collector. This small area in between, that is basically the base, and this area is emitter. Now, when you make this exposure to this this impurity, you make sure that you expose it long enough, so you limit the timing as well as the concentration of this impurity, so that the number of impurity, the dopant particles in the substrate will vary. Okay, so for example, in the emitter, you have more impurities than in the collector region. So they are not the same. They have different concentrations of impurities, right? So therefore, they are not actually the same. Emitter and the collector are not identical, right? So this is basically an NPN transistor. Similarly, you can create a PNP transistor also. So though it looks like this, for our ease of analyzing, let me draw this as a rectangular shape. Okay, like this, with so let me mark it as this. So this is my base. This is my collector, and this is my emitter. Okay, so we know that emitter and the base are of N type, and this is of P type. Okay, so there is a charge bilayer at each of these boundaries. Here you have positive, here you have negative. Similarly, you have positive layer here and negative layer here. So note that I am drawing it asymmetrically to indicate that the depletion layer width is also different. Okay, so this is basically, this looks like two diodes back to back. Okay, so base is something like this. So this looks like this, right? Base, emitter, collector. However, in this simplified back-to-back diode model, this model, it does not capture the fact that emitter and base are not similarly doped. So therefore, that information is missing from this rudimentary model. So any difference that arises from this asymmetry cannot be captured by this simple model. Okay, so something like this, the transistor, the symbol for the NPN transistor is something like this, right? You know, this is the base, emitter, collector. So this is the symbol. This is the symbol of that. Now, if you had a PNP transistor, it would look, the symbol of that would be like that. Okay, this is the base, emitter, collector. That would be the PNP transistor, whereas this is the NPN symbol, right? So let me write down a couple of sentences. A transistor is formed when two NP and PN junctions are produced in the same semiconductor. Crystal, semiconductor crystal, and not joined. The regions are etched into the crystal using diffusion of dopants. Okay, we need to keep that in mind. We don't combine different semiconductors, we just etch them by diffusion. The behavior can be mostly you can see my screen, right?
Yes, sir.
Hello? You guys can see my screen, right?
Yes, sir. We can.
Okay.
Go for it.
Can be mostly described by modeling the transistor as two back-to-back diodes. But an unusual behavior occurs when the two junctions are oppositely biased. In other words, one forward biased and the other reverse biased. So when they are oppositely biased, they behave different. In other words, so you have this diode. If you make this forward biased, in other words, the base is at a higher voltage than emitter, so that the current can flow easily through this, right? So this is the forward bias. And the base collector junction is reverse biased, so that it is in this direction. So current cannot pass through this. So if you model it as two diodes, then what you would expect is, irrespective of what you have in the DC junction, this should have a certain current in the base emitter circuit, depending on the current that you have. But in fact, this is not what happens if you observe the behavior of the transistor. Okay, so that is the importance of this this model. So it doesn't capture the actual operation. So let's see what is the operation of a transistor. Okay. Operation of transistor. Okay. All right. Now, so again, let me draw the figure here. So you have base, emitter, and the collector. They are when not connected to anything, it looks like this. Okay. But when the emitter base junction is this junction, emitter base junction, this junction is forward biased. Let's take that case first. Okay, so this is forward bias, means base is at a higher potential than the emitter, so that the current, if needed, can flow, right? So what happens here is that the electrons here um, can go here and combine with this positive layer, and these negative charges here can exit from here and get attracted to the positive plate of the battery. So what happens here is the current will be in the opposite direction. This is called the base current. This is the current through the diode. And remember, the collector is not connected. In this case, the collector is, not connected to any component. It's open circuit, right? So this basically behaves like a diode. There's nothing new or nothing fancy about this. This is basically the behavior of a diode. If you wanted to use a diode, this is how it would behave, right? So let me put this down. When emitter base junction is forward biased, electrons entering through emitter crosses over to the base. Base. When collector is not connected, base emitter junction behaves as a normal diode. And the behavior can be described using the Eber-Small model. Eber-Small model, right? So this can be represented as two diodes back to back with one connected, the other is not. So this is let me call this the emitter current IE. Okay, so coming out, which is equal to IB also. So this is IE equal to IES. The reverse saturation emitter current E to the VBE divided by N times Vt to the VBE over N times Vt minus IES. So this is the Ebers-Moll model. So this, the current and the voltage applied are, so this is VBE. Okay, so that behaves as expected. However, when the collector is also connected, if I have the collector also connected, and if the collector is at a much higher potential than the base and emitter, so they are connected. So the base emitter are as we had earlier. Now the base, now we bring in the collector also into the circuit, and when you connect it, you put the collector at much higher potential. Remember, emitter is at the lowest potential. Next, you have the base emitter voltage is positive. So the base is at a higher potential, and I put the collector at even higher potential. So if you look at the circuit, it looks something like this. Okay, so you have the base, this is the emitter, this is the base, and this is the collector. Now you already had this connected like that. Now I'm going to connect the collector, and that will be at much higher potential. So much higher potential, right? Like that. So this is how it is going to be in that case, NPN, like that. If that is the case, then this does not behave like two diodes back to back. Now, what happens then is that any electron entering from the emitter, right? So we had electrons entering from emitter. They can end up in three different fates. They can, one is it can simply get out of the base just like what it did earlier. Okay, so this is first thing. Number two is, so remember we had, initially we had this depletion layer. Initially, right? But when you apply this, it changes, remember. But somehow, the second fate is basically you can collide with a hole. So you have holes in here, right? You have holes in here. These electrons can combine with a hole, so that electron nullifies the hole, and the energy in the electron is dissipated as heat. It's dissipated as heat. So this is the second possibility. The third possibility is that one of these electrons can somehow overcome this barrier and get into the depletion layer of the other side. This is the third possibility. The electron could enter the base collector depletion layer. Okay, so there are three different possible outcomes to this electron. Okay, so let me write that down before I continue. But when collector is also connected to the circuit, if collector is at a much higher potential. Remember, these are for NPN transistors. Okay, opposite will be true for PNP. The directions has to be reversed. Electrons entering the emitter end up in three different states. Number one, electron could exit via the base. That's basically what happened earlier. Number two, electron could collide with a hole. In base and lose energy as heat. Okay, so that energy that was in the electron is converted to heat. And the number three, the third possibility, is that electron could enter the base collector depletion layer, depletion region. Okay, so these are the three different possible fates of the electron that enters the emitter. Now, if I want to have this third option without and minimize this first and second options, I want to make as many electrons actually to cross over to the base collector depletion region, and I want to reduce the number of electrons exiting via base as well as the number of electrons colliding with any holes in the base region. What can we do? Now, if you make sure this base, base of the transistor, the thickness of the base region is very, very small. Okay? If you make this thickness very small, also you make the number of holes available in this region very small. In other words, you very lightly dope this so that the number of impurities in this crystal is very small. So by doing these two things, what we can do is we can reduce the number of holes in this region as well as thickness is reduced, so that number 1 and 2, the mechanisms 1 and 2 can be reduced, and we can increase the probability of this mechanism number 3, right? Third mechanism, basically jumping to the other side. Okay? Now we'll see why we do this in a minute. Okay, so let me write, by reducing the thickness of base, we can reduce the possibility of possibility of 1 and 2. Above, and increase the chances of in fact, in transistors, this is basically what we do. Most of the transistors have very thin phase regions, and they are very lightly doped. So therefore, we get most of the electrons entering the emitter to exit, to jump into the base collector depletion layer. Okay, in transistors, the thickness of B is very small. Therefore, most of the electrons entering E, entering the emitter, actually crosses over to the collector. This is not explained by the diode, two back-to-back diode model, and also it doesn't, it is not captured by the Ebersmall model. But this cannot be described by the Ebersmall model. It cannot be described by the Ebersmall model. This is actually because we use an external energy field. So this is basically due to an external energy model. This is an external energy model. Okay, and depending on different, there can be many different types of external energy models. This is one of the external energy models. You need to model this external energy model using some analytical expression if you want to be able to analyze it. Now, how do we capture that? Now, we said by varying the width of the base, it is possible to control the current or the number of electrons jumping to the collector region. So, in fact, it is possible by deciding the by designing the transistor with a specific thickness for the base and the amount of doping, we can control the ratio of electrons jumping to the collector and exiting from base. Okay, so this ratio we call beta, right? So the number of electrons move in motion is a current, right? So electrons in motion is current. So therefore, the number of electrons jumping to the collector side is responsible for the current exiting to the collector. So it is called the collector current. The number of electrons jumping to the base and exiting from the base is the base current. Okay, so by adjusting this thickness, we can control this ratio of collector current to base current, which is called the beta, right? The current ratio. Okay, let me write that down also. By varying the width of the base, it is possible to control the ratio. We call this beta of ratio of current crossing over to collector, that is called IC, and exiting from base, IB. So we can model this external energy field, external energy model as beta is equal to IC divided by IB. Okay, so this is basically nothing but the ratio of 3 above divided by 1. Okay, so that's the ratio. This is also marked as, sometimes we call this HFP. We will see later what this is. So this equation gives you, just like the Ebers-Moll equation gives you the drift of the drift behavior. This basically captures the external energy model. This is the external energy model.